Hi. Good morning. So it's Miss Murphy again. We're going to look into bonding in a little bit different way, more of the properties of different types of bonds and what we would expect to see as the properties of the substances that have these bonds. Okay. So I'm going to go ahead and share my screen. And please take notes. This is simple, but you need to write it down. So it's a study technique. Okay, so let's look at this and just think with me, if you will. Okay, don't get complacent. Just kind of think, and let's call this. I don't want a red. I like the black. Bonding, because bonding is really a spectrum. All right, it's really a spectrum of a degree of sharing. Okay, and recall that whenever we have these bonds, the bonds are all related around electrons. Okay, so we have talked about ionic bonds, and I'm going to put ionic bonds over here on the left side. And we have said that in ionic bonds, we have the transfer of electrons. Okay, what that means is there is absolutely no sharing, right? There's giving and taking. That's not sharing, okay? What we have is we call ionic compounds salts. So I'm going to tell you some things that we haven't talked about yet. We call them salts. NaCl, sodium chloride, is table salt. That is very common, but all other ionic compounds are also referred to as salts. So there are many, many salts, okay? They are solid at room temp. And they are excellent conductors, but not in a solid form. They are excellent conductors when they are either dissolved or melted. Okay, so we're going to learn soon that that is when they are aqueous, means in water, or melted, that's in its liquid state. Okay, so under those situations, your ionic compounds can conduct a current. They can allow electricity to flow through them. The ionic bond is the strongest bond. Okay, and what we have is a crystal lattice structure, so that I have cation, anion, and it's a repeating pattern. Okay. So on the inside of the substance, on a molecular microscale level, this is similar to what's going on, and that causes this to be very brittle. What does it mean to be brittle? It means it does not bend. It shatters, it breaks in fine edges. It doesn't bend and mold. It just breaks. Okay. You can't bend this guy. Very rigid. Okay. And those are some characteristics of our ionic bonds. They have really high melting points, right? Like in order to melt them, you've got to get very, very hot. To gasify them, oh man, I don't even know that that's going to happen. With enough heat, it'll happen. Okay, so there's absolutely, remember we said that bonding is really a spectrum. It's a degree of sharing. Over here with our ionic, we have absolutely no sharing. There is no sharing. So this is the end of the spectrum where there is none, okay? And as we proceed, okay, we end up with some sharing. Some, let's say minimal sharing, okay? And as we start to share, what we end up with is a covalent bond, right? Because in covalent bonds, we know that electrons are shared, right? Electrons shared. So in our spectrum, we've gone from being not shared at all to being a little bit shared. So when we call that a little bit shared, now I need you to think about this. What's a little bit shared? Well, it's I have 10 pieces of candy and I keep 9 and I give you 1. I'm hogging the candy. We're not sharing evenly, okay? That's uneven sharing, uneven sharing. And when we have that scenario, we have what we call a polar covalent bond. So the bond is covalent, okay, but it is polar. And that word polar literally means uneven sharing. So that in our compounds, we have 2 poles, a positive pole and a negative pole, okay? So it would be like this. This is my positive, and this is my negative. Let me do that again because it's supposed to be distorted. That did not look very distorted. Don't do that one either. Let me try one more time. This one will be best. That's better. Okay, so that this is my positive end. And over here are my electrons. So I have a positive side. Oops, no, I'm so sorry. This is obviously, I have a negative, and watch this, guys. I have a partially negative end to the molecule, one side of the molecule. This side of the molecule has a partial, that's what that means. It's an incomplete 8 negative charge. And this side of the molecule has a partial positive charge. And that is due to the uneven sharing. Okay, whatever element is over here, let me put some real examples with this. This would be like F, and this would be like H, okay? Well, F is much more electronegative. So that means he has a much greater attraction for electrons. So that means, and he's much more electronegative. He's much less electronegative. Okay, so when they share these electrons right here, what happens is you see that fluoride really, this guy here, is more electronegative. He has a stronger pull on electrons. So what I want you to envision, if we were in class, I'd be like, I would literally tell you to hold something. I'd be like, here, Jack, you hold the other side of this pencil right here. Like, here's a pencil. And I would stand here and I'd hold it, and you'd stand here and you'd hold it. And I'd say, okay, now I'm going to pull, but don't let me take them away. So there's a tug of war. I'm going to pull over here. So what I'm doing is I'm pulling the electrons to me. I'm not taking them, but I'm winning the tug of war. So I'm hogging them myself. Well, when I pull those electrons towards myself, which the fluoride will do because he's more electronegative, he not only pulls the electrons, but he also pulls their charge as well. So we have a molecule here where in one side, the fluoride side is more is more negatively charged. It's not a full negative charge because he has not taken the electron and become an anion. He is hogging them to himself. So he has taken on a partial negative charge, which causes hydrogen to be partially positive. And I draw an arrow like this. The arrow points towards the more electronegative element. Okay, now I don't need to say some more things about covalently bonded substances like I did over here about ionic substances. Covalently bonded substances share their electrons. This is the weaker bond. It's not nearly as strong as a ionic bond. And because of that, we see lower boiling points and melting points. Okay. They are typically, they're solids, liquids, and gases at room temp. They are poor conductors. Okay, we've got all solids, liquids, and gases are present. Br2 is a liquid. It's the only like pure liquid you're gonna have there that I could think of. I'm sure there's more. Actually, that's not true. Br2 is liquid. Okay, now so go back to our spectrum here. We started with no sharing, ionic bonds. And then we go and we start to share. So now we're calling that a covalent bond. But because our sharing is uneven, we call it a polar covalent bond. Well, as we continue in our spectrum, we get to a place where we're sharing, but we're sharing evenly. Right? So we've gone from no sharing to sharing, but not sharing evenly, to sharing even, okay? Evenly, even sharing of electrons. Yes, so remember, what are we sharing? We're sharing electrons forming bonds between atoms, okay? Now we've got even sharing. So we will call this a pure covalent. So if you ever see that, that means even sharing. We will call it a non-polar, right? Polar means we have the positive, partial positive, and the partial negative end. That's what polar means. It means we have two poles, like a magnet. So if we are non-polar, right, we do not have partial charges. And we would see that occurring when we have elements with very similar electronegativities. Because remember, it's a tug of war, right? It's a tug of war. The element with the highest electronegativity is going to pull harder. They have a greater attraction for electrons. They pull them with a greater strength, okay? Has everything to do with atomic radius, location of electrons, size of the atom. But it is a tug of war. Well, if both atoms have very similar electronegativities, then they're going to pull with equal strength, and we're not going to see the size that atom become distorted. So we would see that like with O-O, right? Both oxygens are sharing these electrons, but they have the same electronegativity, so they're going to pull with the same strength. So we don't have a distorted cloud. Right? We do not have a distorted electron cloud. There are no, and my pen's not working. There are no, let me plug them in. What I'm going to write, guys, is there are no partial charges. Everything's evenly distributed. My pen just stopped working. So let's try that one more time. Okay, everything is evenly distributed. So we end up with a non-polar compound. So go from ionic to polar covalent to non-polar covalent, okay? And we have no, oh my goodness, distortion here. Something's wrong. Let's try that again. Sorry about that. I just wanted to say a couple more things. Doesn't look like I'm going to be able to. Okay. Well, let's just write this down. Ionic bonding is the strongest. Then we actually have metallic bonding, and then we have covalent bonding. I'm not going to be able to get into metallic bonding right now, okay? But it is in the middle of the strength, ionic, metallic, covalent. See you guys, I got to try to figure out what's going on here. Bye.